Today I'm going to show you guys how to make water and sugar out of grapes, marshmallows, and blueberries. So let's get started on that. Hey guys, welcome back to Brain Foods, the educational cooking show where we feed not only your body, but also your mind. And today is a brand new video, brand new camera, and brand new apron. And we're also today going to be talking about atoms and molecules. Everything around us is made up of atoms. They're the building blocks of all matter. And when more than one atom come together and bond, that's called a molecule. Now there's only a few hundred atoms in the world, but there's actually millions and millions of different molecules. So how can that be since molecules are made up of atoms? Well, they're made up of different combinations and sometimes different numbers and amounts of each atom. And so today I'm going to show you how to make some edible molecules. The things you'll need to make your edible molecules are grapes. I've just got 1 pack of grapes. 1 pack of blueberries, 1 pack of mini marshmallows, and some cheese cubes. I've just got some Colby cheese cubes here. You can use whatever kind of cheese you like. In fact, you can use any kind of fruit or food that you want, as long as it's small and you're able to put toothpicks in it. You're also going to need a pack of toothpicks. And so I've got all my ingredients laid out here, and I've got a tray sitting over here that I can set my molecules on whenever they're done. So let's get to making them. Okay, the first molecule I'm going to make is actually a real easy molecule. It's salt, and salt is sodium chloride. It's just 1 sodium atom and 1 chlorine atom bonded together. So we're going to use our toothpicks as the molecular bond, the atomic bond. And I'm going to use 1 of my cheese cubes as a chlorine atom. I'm going to stick that in there just like that. And then I'm going to take 1 of my little mini marshmallows here, and I'm going to use that as a sodium atom. And I'm just going to stick that right at the end there. Just like that. And there. And see how the 2 atoms are bonded together by the toothpick? That is sodium chloride. That's table salt. Now, table salt doesn't necessarily look like this when you look at it through a microscope if you could see the atoms. Because table salt is a crystal, it actually looks a little bit different. So let me show you what that looks like. So if each chlorine atom is bonded to 1 sodium atom, let's say we take a few more of these. Now we take and bond each of these sodium atoms with another chlorine atom, like that. Now if you can see that, see how it makes this kind of lattice square structure? Now imagine that stacked on top of each other, it's stacked on top of each other into a nice square shape, and that is a crystallized form. And that means that table salt is actually a crystal, which if you zoom in on it and look at it through a microscope, you'll see actual little salt crystals. And that's why it's a crystal. Now actually water is the same way. Now let's look at water. Let's pull these off to the side. Let's look at what water is. Water is H2O. That's the chemical formula for water. Now what that means is it has 2 H, H2, and 1 O. So that's 2 hydrogens, H, and 1 oxygen, O. So let's take our grapes, 1 of our grapes for oxygen. And let's stick 1 bond on that side and 1 bond on that side. And then I'm going to take, and this time instead of the marshmallows being sodium, they're going to be hydrogen. I'm going to stick that one on there and stick that one on there. Alright, so here is our water molecule. 1 oxygen and 2 hydrogens. Now, you may notice that my bonds are at an angle like this, like little feet. See, you go walking down the street. Now why did I do that instead of putting one hydrogen over here and one hydrogen over here? Well, it has to do with the way that these atoms are. You see, these hydrogen atoms are actually negatively charged, and the oxygen atom is positively charged, which means that the negative charges are going to be on one side, opposite of the positive charge on the other. Now, I know that seems kind of complicated. That actually means that this is a little tiny magnet, because magnets have a positive side and a negative side. And that's important for the way that water behaves on the molecular level. In fact, let me take you over to my whiteboard and show you a little bit about water and how the molecules work. So what exactly is so special about water molecules? Well, as you can see here on my whiteboard, we have a water molecule, one oxygen atom and two hydrogen atoms. Now, like I said when I was making my little model, each one of these has a positive and a negative side, meaning they're like little tiny magnets. They send out these little magnetic fields and attract other water molecules. Now, what does that all mean? Well, it depends on what state the water is in. If it's in its liquid state, which is water, which is what this looks like, all of the atoms are kind of mingling amongst each other. They're all kind of just freely moving around any which direction they want. The magnetic bonds are kind of strong, but they're not bonded really strong. But what about steam? Well, let's take a look at what happens in steam. As you can see here, the molecules are spread out really far, and there's a lot of space in between them, and they're just kind of moving all around each other. You do have some magnetic bond between the different molecules, but that bond is really weak. But there's something special, and why this magnetic bond between these water molecules is so important is when you start freezing it. As it gets really cold, these molecules start to form a special type of lattice, which is what this is right here. The magnetic bonds between these atoms are really strong. But if you notice, there's a lot of space between each of the molecules. Now, what does that mean? That means that ice is actually less dense than water, because there's a lot of space in this lattice. Why is that important? Well, let's say you had a glass, and you filled that glass with water, and then you dropped a couple of ice cubes into that glass of water. What would happen to the ice? Would it sink down to the bottom? Well, no, it'll actually float to the top, float on top of the water. Now, why does it do that? That's because the ice is actually less dense than the water. So now that you guys have learned a little bit about water molecules, I've also finished up the 3D salt molecule here. So you can, as you can see here, it's 3D. It's a crystalline shape because it's all bonded together in this nice, perfect little lattice shape. So now that I'm done with these molecules and they look so cute and cool, I'm going to set these off to the side and I'm going to work on a more complex molecule, a sugar molecule, just plain old white table sugar. To do my complex sugar molecule, I printed out this special little template here, and not only does it have the diagram of what the molecule looks like, but it also lists out how many of each atom I'm going to need. And so for sucrose or sugar, regular table sugar, I need 12 carbons, which I'm going to use grapes for that. I also need 11 oxygen atoms, and for that I'm going to use blueberries. And I also need 22 hydrogens, and I'm going to use the mini marshmallows. Now, because some of these bonds for these atoms are closer than some of the other ones, I'm going to use a pair of scissors to cut my toothpicks down to size. So let me get started on making this. Alright guys, we finished our sugar molecule, this is what it looks like right there. We've got all of our atoms bonded together, and this is what normal white table sugar looks like on a molecular level. It's the kind of sugar that you normally add to your tea or to sweets or whatever, what candy's made out of. That's what this is. But what's interesting about this molecule, which is sucrose, is it's a disaccharide. Now that's a pretty big word, and what it means is it's made up of two separate molecules bonded together to form one new molecule. And the two molecules that are bonded together are glucose and fructose. Alright guys, here are the edible molecules that we made today. We've got salt and sugar and water and all the little molecules that we made. And these things are real easy to make, so you can make them at home. Just remember to take the toothpicks out. Don't eat the toothpicks. And you can actually use these as party snacks. You can just set out a tray with all the ingredients, and then people can put the toothpicks and make their own little molecules. You can use whatever you want. You can use strawberries, raspberries, anything that you want. If you can stick a toothpick in it, it can be a molecule. I will be posting pictures of these all over my social media, so you can check out my social media, my Twitter, my Facebook, my Pinterest, all of that. There will be links in the description down below. You can check it out. If you guys want to make these and send me pictures of them, because I really want to see what kind of little molecules you make. Also, you can look online and find some models and some diagrams of other molecules, not just the ones that I made, and you can try making those and send the pictures of those to me too, because I would love to see those. And if you send me those pictures, I will put them into my outro screen, so everybody who watches my video will see your pictures in my outro screen. Be sure to hit that big red subscribe button so that way you don't miss any of my videos. Be sure to like this video and also share it with your friends. If you know friends who love science, who love learning, and love to cook, this is the show for them. So I will see you guys next week. Bye-bye.